Good evening. Let's solve another example in concrete structure, this time in T-shaped section. So let's assume we have a T-shaped section and we want to analyze it. It's like a continuous span, and let's go through this problem. So in this problem, in the part A, we want to determine the effective depths of below section, and in part B we want to compute the design moment capacity, which is phi times mn. Provided F prime C, specific strength of concrete 4,000 pound per inch squared, and grade 40 steel which has a yield strength of 40,000 pound per inch squared. So in this problem, let's see how we can solve the problem. So a 3 number 10 is equal to, each of them AS is equal to 1.27 inches squared for each of these number 10 rebars, and we have 3 of them, so the total still is 3.81 inches squared. We want to find the effective widths for one of these T-shaped sections. So let's see how we can approach it. So BE effective widths is the minimum of BW, BV plus 16 times HF, which is provided, and BW plus SN, SN is 60, and BW plus LN over 4, LN is equal to 24, and LN is like this one. If alongside the road we have one other of these section and just go on, the road goes on, and this is like center to center, that's LN, which is 24 times 12 in terms of inches. And then the minimum of this 12 plus 16 times 360 inches, 12 plus 60 SN, and BW again 12, which is here, plus LN, which is these distances, and 24 times 12 over 4 gives us 84 inches, and the minimum definitely is 60 inches, so we can simply pick our effective widths, and as soon as we have effective widths we can go to the second part to see if our section needs the calculation of a T-shaped section or not. So we do know if our A is less than height of flange, is a fitness block of stress is less than height of flange, it doesn't enter the domain of web, so we don't need the T-shaped section. So in that sense, A is equal to 0.747 inches, and HF is 3 inches, so we don't need any AH. A is smaller than height of flange, no need for T-shaped calculation. Section acts like a rectangular section with the height of, or effective depths of 24, like it remains the same, and effective depths which we already calculated in part A, which is 60 inches. So Mn is area of steel Fy times the arm D minus A over 2, like a normal rectangular cross section, and it just gives us Mn is equal to 3601 kilopound inches. Converted to feet, it just gives you almost 300 kilopound feet. And then for ductility check, you need to go through C is A over beta 1, gives you this amount of neutral axis. C over dt, which is again 24, gives us this number, and that's smaller than this number, which is for grade 40 steel. And tension control section, that you can use phi equal to 9.9. Phi times m, and design moment is 0.9 times 300 gives us 270 kilopound per feet. And then we need to also check ACI for requirement of row minimum. Again, F prime C is 4,000 less than 44, so this number is controlling the maximum of these two. Our row minimum is equal to this one, and then we can double check all row available should be bigger than row minimum. Row available is AS over BW. Don't forget to for effect. Also, we consider our section like a rectangular section, but in the real case we have a web and a flange. So this is our web and this is our flange. Don't forget to consider the effect of your B for B web, then times D. That's 12 times 24, and it simply gives you this number, which is definitely smaller than or bigger than row minimum, which is 0.005. So that's again requirement for row should be bigger than row minimum to avoid to using something like a cosmetic steel amount. It's a structural steel. Thank you. We'll solve more problem in next videos. Thank you.